Session. So, ladies and gentlemen, esteemed colleagues, and enthusiasts of space exploration, welcome to today's session on understanding the NASA systems engineering process. In the next the few hours, we will delve into the intricacies of NASA's approach to systems engineering, a critical framework that underlies the success of some of humanity's most remarkable space missions. NASA, the National Aeronautics and Space Administration, has been at the forefront of space exploration for decades, and its achievements stand as a testament to meticulous planning, innovation, and the application of robust systems engineering principles. This session aims to provide the participants with a comprehensive understanding of the NASA systems engineering process, shedding light on its key components, methodologies, and the role it plays in the success of space mission. System engineering is the interdisciplinary field that focuses on designing, integrating, and managing complex systems throughout their life cycles. In the context of NASA, this process is paramount to the success of missions that involve cutting edge technology and intricate spacecraft and ambitious objectives. Before we start Mr. George's session, I would like to give a short introduction about him. So, ladies and gentlemen, it's with great pleasure and honor that we welcome our distinguished guest speaker for today's session, Mr. George Salazar, a luminary in the field of electrical engineering and systems engineering. Mr. George brings over 40 years of unparalleled expertise and innovation to our discussion. Mr. George commenced his academic journey at the University of Boston, earning a Bachelor of Science in Electrical Engineering, a foundation that laid the groundwork for the remarkable career. Not content with just one degree, he furthered his academic pursuits by obtaining a Master of Science in Systems Engineering from Southern Methodist University, showcasing his commitments to continuous learning and mastery of multiple disciplines. Throughout his illustrious career, Mr. George has become a beacon of excellence in various domains, including telemetry, communications, and speech control, command and data handling, audio, displays and controls, intelligent lighting, project management, and systems engineering also. His extensive contributions have been recognized with multiple inventions patents, underscoring his commitment to pushing the boundaries of technological advancement. Currently serving as the Human Computer Interface Technical Discipline Lead at NASA Johnson Space Center, Mr. George holds a pivotal role in shaping the future of exploration. His responsibilities include the development of advanced human interfaces for monitoring and controlling spacecraft, a task that demands both precision and innovation. At the end, I would like to introduce to the motto of Mr. George, exploring the cosmos through precision and innovation, unveiling the NASA system engineering tapestry. So now I would like to hand over this session to Mr. George, and also thanks a lot for joining us today, and over to you, sir.
All right. Well, thank you very much. I'm going to attempt to share my screen here,
Yeah, yes, sir.
hopefully. Uh, okay. Can you see that?
Yeah, yes, sir.
Excellent. All right. Well, good evening over there, and good morning from Houston, Texas, in the United States. Thank you for giving me the opportunity to, share some knowledge with you about some of the things I have been doing at NASA. And one of the things that really involves quite a bit of, let's say, experience over the years is understanding the NASA systems engineering process. And so there's no way I can share everything I can with you about that process. But what I wanted to do is just kind of give you a big, brief overall view of what the NASA systems engineering process is. It's not, let's say, unique to any other disciplines, but it does have its differences in some areas, just simply because we develop spacecrafts as opposed to uh, jets or cruise ships or uh, automotive cars or things like that. So what I'm going to do is let's see here. Hopefully the yeah. So these are the topics I'm going to talk about. First of all, I'm going to talk very briefly at a very high level about the system complexity of future space missions, and this is something that we are challenged with. Is the future missions are much more complex than what we used to do back in the days of Mercury program, Gemini program, and to some extent the Apollo space program, space shuttle, space station. So, understanding complexity and how to deal with it is important. And that's where the importance of NASA systems engineering process comes into play. And that's what I'll spend just a few minutes talking about. And then I'm going to start getting into the NASA systems engineering life cycle because it's basically a series of processes that we go from the very beginning of the program to the very end of the program. We sometimes call it from cradle to grave. I think for a lot of our programs, we've had that. For example, the Apollo space program, we started early and then we finished it. Um, so I'll be talking about the life cycle of the NASA systems engineering process, and then I'm going to talk about the key processes involved as part of the systems engineering life cycle, and then I'm going to summarize, my presentation. So let's just kind of briefly talk about, what is the top level, let's say, uh, view, what we envision in terms of going to Mars. And so what you're seeing here is different phases. And right now we're doing this one, what we call Earth reliant, phase zero. This is where we're learning to live and work in outer space, and that's why we have the space station orbiting around the Earth at 240 nautical miles. Then we're going to start it. We're advancing our technology on the space station, along with advancing technology here on Earth. And then now we're going to the proving ground. So the proving ground is the moon, and the program that NASA has for that is called Artemis. And it's basically returning to the moon, but this time to stay for a long period of time, as opposed to the Apollo space program that we went. I think it was 6 times landed on the moon, and then came back home, and that was it. Altogether, we spent about 3.5 days on the moon. With all those missions that we had, That's all we had. We had not much time, so we need to learn a little bit more about living on another planet for a long period of time, especially if we're going to be going to Mars. Okay, so Mars is a little bit more challenging, just simply because it's further and much further away than the moon. So emergencies and things of that sort can become very troublesome if we have to rescue astronauts on Mars compared to the moon. The moon is only about 2.5 days to do a rescue, whereas Mars, we're talking months. So what you're seeing here is an incremental process of eventually going to Mars. And this is, let's call it really big systems engineering because we're breaking up the pieces to incrementally improve until eventually we get to Mars. So um, let's see here. Mission control. Right now, mission control has somewhere in the vicinity of 250 people that support people on the space station. Eventually, we're going to have people on mission control supporting the moon program. And the thing about right now the mission control center is that it's able to help very quickly, within a few seconds. it's going to change as we start going further and further into space. And so we can no longer depend on mission control to help astronauts. Astronauts are going to have to help themselves along with the spacecraft system's capabilities. And so we're going what's called crew mission control dependent, mission control being the one on the ground, and the crew with the vehicle, to something that's new to us called crew vehicle dependency, where we're going to have to rely on spacecraft systems, to help the astronauts. And of course, things like artificial intelligence, machine learning are going to be important. But there's some challenges associated with that kind of technology, just simply because of the computing power necessary to do that, and that the radiation environment makes it difficult to have these kind of systems operate in deep space. So let's now talk about system complexity. And this is something that I guess I didn't learn in school, or they didn't teach it in school. But the thing about system complexity is that it makes developing systems very complex. And space systems are getting more and more complex. We're looking at spacecrafts, like for example, there you're seeing the Hummer lander systems, provided by SpaceX and pretty soon Blue Origin. We're talking about the Orion spacecraft. The Orion spacecraft is where it's going to carry the astronauts to lunar orbit and dock with what's called the Lunar Gateway, which is kind of like the lunar space station, if you will. Then we got surface systems. Surface systems are like, for example, habitats, extra vehicle activities, spacesuit, people walking in spacesuits on the moon. We have rovers. We have all kinds of experiments. So there's going to be quite a few server systems, and this is obviously an area that a lot of international partners, and I'm sure many countries such as India, and I'm sure Pakistan and other countries are going to get involved over the years. And then, of course, we've got the launch systems, Space Launch System, which launches the Orion spacecraft. And of course, we also have SpaceX that has its own heavy booster as well, that I think eventually is going to be also helping in landing stuff on the moon. Um, so the interaction in complexity increases as the number of what I call here N elements that make up the system start to increase as well. So think about the elements such as electronic computers or sensors, mechanisms like rotors and motors and things of that sort. Of course, software, just an incredible amount of interaction in the software. And of course, you got the human also as part of that interaction. So if you see here, kind of simplistically, if you only have two elements, it's just only one connection, pretty much. So you communicate with one entity to the other, and then the other back to this one. As you go to three, you have more connections, and of course, as you start increasing the number, the inner connectivity and interactions increase dramatically. So think about interacting with different disciplines, different experts, but also dealing with development of different elements. And you can see how much information has to flow and flow correctly to making sure that the end system is going to perform its intended function. Um, Understanding the system requires how it's going to be used. Okay, where is it going to be used in space? What part of space? What's the mission? Uh, the environment is going to be used in. For us, it's obviously space. But wait a minute, space has different environments. We got let's say the orbiting environment around the moon. We got the surface orbits, or rather the surface environment. We start going further into space, like for example, Mars, its environment is different than the moon. So as part of the system complexity, we have to understand the environment and the mission that it's performing, and understanding what technology and knowledge do we need to go there and perform the function that we're looking for. as we're getting into more complexity, we have to look at a different approach in developing systems. We have to look at something called decomposition, making the pieces more manageable. There to the right, you see a picture of a Tesla automobile with all the pieces that are associated with it. And you can see that there are a lot of pieces to develop individually and then eventually put the whole thing together to make a car. And same thing happens with a spacecraft. So dealing with this kind of complexity is not simplistic and it's not hard. You have to look at things like level of extraction. So what does that mean? That means you have to look at it from a requirement standpoint and behavior. How does the system is supposed to behave? Then you have to talk about what kind of methodical formal analysis that we have to do. And there's something called model-based systems engineering that actually is very helpful in let's say simulating and emulating a spacecraft with all the different pieces. That easy. It takes a lot of, as I mentioned previously, that the it's through decomposition. So you see a picture here of representing a complex system made up of all different subsystems. Like for example, space shuttle. Oh my gosh, it had the thermal system, propulsion system, the life support system, the avionics system, the uh, reaction control system, just a whole bunch of systems that made up the space shuttle. Well, it's very hard to understand the whole picture, but if you start breaking it down into the subsystem, like for example, here's a subsystem made up of its pieces, and then you break one of those pieces down to even further level, which is like for example, a flight computer or component. Now you're gaining a better understanding of the complexity of just that piece and how it relates to the big picture. So this decomposition becomes very important, especially for the NASA systems engineering process, in order to understand how are we going to tackle such a complex vehicle or a complex system, um, and build it correctly. So applying a methodical and disciplined approach to developing complex systems is part of systems engineering. It's systems engineers multidiscipline. You got engineers from all different areas, thermal. You got structure people. Um, you have people from the materials world. You have people from the propulsion world. You got all these people interacting along with scientists that are doing some of the research and some of the groundbreaking, let's say, investigations of how best to go to another planet, or how are we going to gather data from another planet using some kind of remote sensing. All these people are working together as part of the systems engineering process. And again, keep in mind that picture that I showed you previously of interactions of all these people talking to each other. It's systems engineering is rigorous in terms of the design, implementation, and operation of a system. And keep in mind that different teams are developing different systems with different requirements, both functional as well as non-functional. What are functional requirements? Like, for example, there shall be audio, there shall be video, there shall be a hand controller for the astronauts to control the spacecraft. And then there's the non-functional requirements, like, for example, reliability, or must operate in the lunar surface, dealing with dust and things of that sort. So all these requirements are huge for each one of these different systems. And for the most part, here's kind of a simplistic breakdown of what each system has to go through. And so you got the needs and goals of the system. What are we trying to do? What are we trying to accomplish? And then also there's a area that we have to make sure we have to address, and it's called feasibility assessment. Will will we be able to build something that complex? Is it going to cost too much? And I'll show another chart later about that. But the feasibility assessment becomes really important. And then, if everything works out okay, you start developing draft requirements, draft specifications, looking at constraints, size, weight, power, cost, schedule, all those kind of things become part of the big equation of how we're going to build the system. And then you apply the systems engineering process, the formal systems engineering process that eventually will help build the system in terms of the hardware elements, the software elements, and the human elements in the mission the system was designed for in the operating environment. So you got different end items here that you're trying to develop a system to meet all the requirements dealing with those interactions. And of course, just to bring back a picture of all the different systems, each one of these has to go through that whole process. Um, Also, if these systems are interfacing with each other, you have to think about ensuring that the integration of the different pieces come together. Like, for example, right now we're working on the Human Lander system where the Orion spacecraft is launched by the Space Launch System, and then SpaceX launches the Human Lander system using their heavy booster. And then they go into orbit and then they dock the Orion spacecraft with the Human Lander system. The people, the astronauts in the Orion spacecraft space capsule crawl into the Human Lander system, and then the Human Lander system undocks from Orion and then goes down to the surface of the moon. And then when they're done doing their experiments, they come back up and then they dock. The people in the space Human Lander system get back in the Orion, and then from the Orion they go back to Earth. And so that's part of the mission concept. But all these interfaces have to work, and that's another piece that is a challenge as well. So for the Artemis preparation for Mars, I'm just going to briefly mention that, this is kind of an evolution, if you will, of how the increment, we're going to be incrementally developing capabilities going from just basically testing and landing ascent capabilities all the way to eventually preparation for Mars, where we build a deep space transport system that takes humans to Mars. And then at the same time, we're developing many capabilities on the ground. Okay, as I mentioned, we have lunar terrain vehicles, we have habitats, we got mobile vehicles here, and of course, astronauts doing extra vehicle activities in order to perform experiments or maybe build things on the moon. But it's a learning experience, and that's a key aspect is to learn how to live on another planet where we can no longer depend on Earth, to help. Um, so the increase in mission complexity is going to be dramatic, going from just more from understanding the fundamentals, if you will, of going to Moon all the way to going to Mars. Even that's going to be more challenging. So, but that's part of systems engineering. And systems engineering is, if you think about what all I've mentioned, you say, my gosh, there's all kinds of risks. Yeah, there's a lot of risk in a program. When you first develop a program, you have kind of an iceberg. I like the iceberg analogy because, like, for example, when you develop something, you have an expected behavior. And this is something that I came to learn that I build something and I say, well, I understand how it operates. But then when you start adding things to it or interfacing with other components, the behavior starts to change. And there are things that you weren't expecting. And so as you're developing this, especially with the human, the challenges get quite large, and more so the risk. So, what kind of risks do we have to deal with? These are the risks that we don't know about yet until we start developing our system, and then we start learning. Oh my gosh, we got some safety risk associated with the human. We got technology risk. I didn't realize that this technology was going to take this long to build because it's very difficult to build or very difficult to test or whatever. So you get those kind of risks, and then cost risks. All of a sudden, the government, in case in NASA or private company, they say, well, we don't have the money to do everything that you want. We can only give you this much amount of money. So now you say, oh my gosh, I'm constrained with limiting what I can do. Schedule risks. You're under pressure to like for example going to Mars. You only have certain windows going to Mars because of the orbital mechanics where the Earth is relative to Mars, and there's only a certain period of time, roughly about 2.5 years, where the Earth and Mars are the closest point, and that's what you're trying to target. So your schedule, your risk is schedule risk there, and then contract risk. Sometimes it's a problem, especially with NASA. You're dealing with companies that sometimes, uh, let's say, don't produce what they said they were going to do, and you end up dealing with how are we going to recover if we no longer have this contractor doing this work for us. And so that's another risk we have to deal with. But I have to say, for the most part, we have not had that issue, at least in the space program, except for one that I remember, but it was a very small contract risk. Uh, so let me start getting into the program project lifecycle right now. And so this comes out of the what's called the NPR, NASA Procedural Requirements 7123.1D. This is the NASA Systems Engineering procedures that every NASA center, and we have about 12, no, 10 or 12 NASA centers, and each one of those centers develop major programs. JPL, for example, Mars Lander, Goddard Space Flight Center, along with Glenn Research Center, developed things like James Webb Telescope, and of course NASA here in Houston, where I work. We develop human spacecrafts. Like for example, we developed all of the Mercury, Gemini, Apollo vehicles because they had humans inside. Currently, we're developing the Human Lander System as well as the Orion spacecraft system. So each one of these have a life cycle phases that they go through, and that's what you're seeing, up here at the top. Uh, there's a there's the robotics mission, and then there's Human Lander System. Of course, this is the area that we deal with. The red ones are milestones that have to be met in order for ensuring that the system is being developed within cost, schedule, and technical risk. And then, as part of that, are what we call the life cycle phases. Starting from phase A, and I'm going to go through each one of these. Phase B, phase B, C, D, E, and F. F is where they basically close out. Um, I think right now, space station, they're ready to close it out somewhere in 20 and 30, which means they're planning on basically re-entering the space station into the Earth's atmosphere and basically dissolve it, if you will, in the Earth's atmosphere because it's reaching its end of life. And that's what phase F is about, end of life. How are we going to close out the project? Up here, there are basically the key phases. Okay, so we got a pre-formulation phase, and then we got a formulation phase, and then we got an implementation phase. Along the line, we have what we call KDPs, key decision points. Are you ready to go to the next phase? If you are, you can do what is required here, and then you go through another key decision point, and these are very high level and many days of reviewing data to make sure that we are ready to go to the next phase. And so these key decision points are critical to making sure that the mission, or rather the development, is ongoing. as part of that, there's different reviews going on, and I'll mention more of that later in my presentation. But these are kind of like key milestones within each one of these phases to making sure that everything is going okay within that phase. If it's not, we have to kind of like back up a little and try to find out what's going on and see can we fix it. So we go from a approval of formulation, an idea. I got an idea of going to Mars. I got an idea of building a telescope or whatever. And then you go through these all these phases. You go to a system implementation. That's where you implement the system. So going from here to here is not easy. It takes a lot of effort. So let me just kind of go next into what's called pre-phase A. So pre-phase A, and it's up here, and I have a kind of a running tally up here at the top of what phase I'm talking about. So pre-phase A concept studies, and there's a lot of major events, and I'm not going to talk a whole lot about these, but it's an opportunity to see if what we want to do, go to the moon, go to Mars, or build a spacecraft that goes to Jupiter or whatever, can it be done? Okay, so we go through a whole bunch of procedures looking and investigating whether it's possible or not. There's something called scoping, and scoping basically addresses these areas right here. Feasibility, the most important one. Cost and schedule, obviously, is key too as well. And then looking at alternatives for the mission. So in scoping, you look at, okay, who's going to be responsible for what? We want to make sure we know who are the key players are and what's their responsibility. But first and foremost, what are our goals? We're going to go to Mars. We want to land on the moon or whatever. What are our objectives? What are we trying to accomplish? What's the mission? What's the mission like? Constraints? Are we constrained by how long we can stay on the surface of the moon or on the surface of Mars? And then we look at some assumptions. Sometimes we don't have all the answers, so we have to make some assumptions. But once we've gone through all that and we think we have a good handle on this, then we draft what we call preliminary system level requirements, and then we identify potential technical leads. And there's something called technology readiness level that NASA uses, and it's basically let's call it a thermometer of some sort to measure how mature is the technology in terms of its application. And so we go from TR level one, which TR level one is kind of like you're in a research laboratory and you're developing something on the workbench. Very simplistic, but that's very low level technology. All the way up to nine being it's actually flying in space, and it's been flying for a while now. I have to say that most of the technology that we deal with, we want to make sure that we are way above TR level one and two. We're more like three, four, and five. So just simply because by TR level six, at TR level six is basically we have demonstrated that the technology will operate in the relevant environment, not the actual environment, but relevant. What does that mean? That means that we've tested in the temperatures expected. We tested in the vacuum expected. We're gravity expected. All these things, and so we've tested all that. But we're also dealing with technology with the human, and of course that's a huge one. We have to deal with altered gravity. What kind of technology do we need to keep the astronauts from losing a lot of bone because of being in a microgravity environment or low level requirement? Space radiation, that's a huge risk. As how do we protect the astronauts? Because space radiation is just not dealing with them potentially getting cancer, but it also affects their cognitive neurological system, which basically makes it difficult for an astronaut to think, if you will. Isolation and confinement, more psychological. You're far away from home, you're far away from family. What does that do to you? How does that affect your performance? And then obviously you're in a hostile, closed environment. Obviously, there's no air on the moon, and so you have to provide that. You have to provide water. You got to provide food. And so you got to deal with that kind of technology. And then distance from Earth is also a major thing. And so things like medical emergencies, how do we deal with that? So all these things come into play during our pre-concept phase. So the key takeaway here in pre-phase A is it feasible? Uh, is it within the cost and schedule? And can we develop the technology for implementing this particular mission? So there's this big uh, meeting called, basically key decision point A. And key decision point A says, okay, we looked at this, we looked at all the information that you provided, we looked at all your research and all this kind of stuff. We give you approval and money to go to the formulation phase. Okay, so now you can go to the formulation phase where you start getting more refinement of your system. So again, I'm showing here uh, basically the systems engineering NASA. We call it the NASA Systems Engineering Engine. And so there's two, and I break it up into what's called a V. So on the left-hand side of the V is system design. So we look at stakeholder expectations. What are who are the customers? What do they want? Technical requirements. How do we come up with the specific technical requirements of the system? And then there's other things here that I'll cover later, but logical decomposition and analysis basically is developing architectures, different architectures that will do the job, but may cost more, may not cost more, but it's an opportunity to do trade studies, and trade studies is a big thing at NASA. And then you come up with a specific design solution. This is the design that I want to use. Then you start getting into the implementation and you start building this hardware systems, and then you start integrating the pieces. Then you do verification, validation. I'll say more about that later. And then you transition to the next phase. So transitioning to the next phase is like, for example, I built the Orion spacecraft, and now the Orion spacecraft is going to the Space Launch System, so we can integrate the Orion with the launcher that's going to launch the astronauts. So let me go back to concept and technology development. Major events here. Again, I'm not going to say a whole lot about this. There's quite a bit of stuff, but some of the key aspects here is the systems requirements review, as well as systems development review within that formulation phase. And so to get to that point, you have done a lot of early prototyping testing. You've done a lot of testing in terms of things that may or may not work. Look at alternatives. You're developing baseline plans. Okay, here I think it's what we need in terms of testing this technology. Here is here's my management plan. So management plans include and back over here there was I forgot to ask, or rather forgot to mention, that there's cost cutting technical management processes that oversee this. And so part of it is rich management, configuration management, interface management, which is the biggie. And so all these are happening simultaneously. If you notice, there's something here you'll see throughout my presentation. It's called hazard and safety analysis. And this is done constantly, making sure that we have not overlooked something that could cause a hazard to the astronauts. Um, and of course, the key takeaway from all this is that our initial requirements, our initial architecture, we think we're going in the right direction, and it is going to work as expected. So then you go now to another key decision point. Okay, you've shown all this work, you got all this documentation that shows what you're going to have to do. You even include the human systems integration plan. How to integrate the human into the system, and so you also have a good idea of the concept of operations. Sometimes we call it ConOps. What is the mission going to do? What's required? What happens when? Things of that sort. So, the decision makers look at all this information, and if everything looks good, they give approval to go to the phase B part of formulation, which now gets more into the refinement of a specific design. So in the phase B preliminary design, we're down here in the logical decomposition. We now have quite a bit of information on a particular design. We've done quite a bit of studies and testing and things of that sort. We've done even developmental testing. We've done testing in vibration. We've done testing in radiation, uh, and uh, and we've also done quite an extensive analysis in taking a requirement to the and the behavior and the structure components. So basically, the requirements are the basis of behavior. And just think about software, how a let's say a robot is supposed to behave. So the behavior usually is in software, for example, but the behavior is derived from requirements. Okay, so we have to make sure that we have documented that the requirements are going to create a certain behavior of the system, and then that behavior is now we determine, well, how are we going to create that behavior? Are we going to do it in hardware? Are we going to do it in software? Or are we going to do it in the human? And so the function and interaction of that behavior is allocated to either structure, components, or the human. And then you go back up to verify that you did it correctly. Okay, I got all these components and structure. Are they going to perform the behavior? That's another part of the analysis. And then the behavior is now based on the requirements. So the behavior should really reflect the requirements. So if the requirement is that at 10,000 feet a parachute will deploy, that behavior in software and hardware should reflect the the implementation to for that particular requirement. And so, again, here's some of the developmental testing that we do. You got the vibration, electromagnetic interference, which is a biggie with electronics, vacuum, thermal, radiation. Radiation is a biggie again with electronic components. And then we're doing quite a bit of performance margin analysis. We're always designing a system to operate well within its capabilities. Like, for example, if you have, let's say, a computer component that it says in the specifications can operate from 0 degrees Fahrenheit, 0 degrees Celsius to 100 degrees Celsius. You don't want it. You don't want it to see 100 degrees Celsius. That's the very upper end. So you design a system that it only sees 50 Celsius. Okay. So in other words, you cut the margin of its operation and giving yourself 50% margin. So in other words, you're safe well within the operating temperature or operating characteristics of the component. Um, and then there's also in the preliminary design, you're doing this iteration, sometimes called human-centered design, especially if you got an astronaut. You got a design solution. You're doing analysis of human error, and not necessarily that the human made the error, but there's something in that system that can cause an error or some kind of hazard to the mission. Human in a loop testing is something that we do quite a bit of. These astronauts will take a actual system and operate it to see if it's doing what it's supposed to be doing. Going back to behavior, that system has a certain behavior that's been designed to do that, and the human in a loop test verifies that. Then you make the assessment: is this right or not? And if not, then you improve on it, and you go back again. So in the preliminary design, the kind of the big takeaway is that you've done more and more refinement of a particular design that you have homed in on. That was something that you did as part of the trade studies. You looked at alternatives, you looked at different systems, you look at different architectures, and you said, but this one is going to be the best because it's going to meet the cost, it's going to meet the schedule, and it's going to meet the technical requirements. And some of the technical stuff we can improve and mature over time, that it'll be ready for the mission. So at that point, there's another key decision point. Have you done all your work in order to go to phase C? And phase C, you see all these dollar signs? It gets very expensive over here. Now you're starting to really burn money very quickly. I don't want to say burn money, but things are costing things are getting very expensive now. So at key decision point C, the completeness, consistency of the planning technical baseline formulation has been done, and now we're going to go into implementation. Keep in mind that um, we're trying to make sure that everything is done the best that we have done in terms of designing the system, because we're trying to avoid redesign. Redesign gets very expensive in the implementation phase, and that's why actually a lot more rigor involved than I show here. But I'm just kind of giving you a flavor of some of the things that are involved during this phase, to making sure that the design that has been selected is going to do what it's supposed to do, and that everybody has confidence that this is going to come together properly. So the next phase is a critical design review, and that's down here at the bottom of the systems engineering process. And for the most part, this is just a refinement of the preliminary design. You're going to more level details. You're going into critical design of subsystems. You're going into more detailed analysis of your design, your structures, your materials. You're going into more testing. You start doing things like even outgassing. Outgassing is something that's done with spacecraft system, just simply because they a lot of the non-metallic materials will produce a vapor that could be harmful for astronauts or flammable. And so we have to make sure we do testing. We have a facility in New Mexico that does that, not, just next door to the state of Texas. Uh, the launch systems and crew readiness review are done. So we're getting into the details. We got people that are looking at the actual code, basically line by line, and they have obviously tools, to analyze that, circuit schematics, mechanical schematics, looking at the details, structures. They have things, structural analysis, fatigue analysis, all these kind of things that are involved with structures. We're also, and this is a big one that sometimes is not advertised, is cabling. How are you going to cable all these connections on a spacecraft, and how are you going to do it neatly? And also, how are these cables going to survive the environment that they're going to be exposed to? So cabling is a big thing. Here's a picture of the space shuttle um, uh, flight computers and all the cabling that went from the flight computers to the different parts of the space shuttle. Incredible amount of cabling, somewhere in the vicinity of 400 miles of cabling went into the space shuttle. Um, and then you're looking at things what we call technical performance measures. These are kind of like measuring guides, if you will, of how well are we developing something. So, like for example, I think this one here shows vehicle weight. So you say, okay, I think it's going to weigh this much at this point in the phase of the development, but by the time we get to implementation, it's going to weigh this much. But along at the different phases, you're constantly weighing it and seeing how much weight does it have. So you're hoping that you start out with a line like this, and then these are your margins that you see right here. If you start, let's say this line started to go upward, you got a problem, and so you got to go back and assess what's going on. So once we've done all this, again, we go to key decision point D: completeness, consistency of all the planning, the technical, the schedule. Uh, Another one is, have we done a lot of the detailed analysis, and do they have margin? Margin is a big thing with NASA, especially when we're getting to develop a flight system. So we proceed to phase D, and in phase D is uh, the integration, verification, validation. Just let me say real briefly, there's a difference between verification and validation. Sometimes these terms are used interchangeably, and they're not. Verification basically says, did we build the product right? Okay. Did we build it to the specifications? Is it going to operate in the environment that we designed it for? Validation says, did we build the right system? Is this going to do what we're looking for? And so there's a big difference between verification and validation. But this is the kind of testing that's done to verify that the systems are ready to go. We're building, we're taking all the components, they're being fabricated, and then all these pieces start coming together. We start doing integration testing at the subsystem level, and then at the system level, and then at the vehicle level. While this is also going on, we're doing a lot of human in the loop testing with high fidelity facilities, making sure that the flight systems are actually performing the behavior that was originally designed into that system, and the astronauts know and understand the behavior of that system, and nothing strange is starting to happen when they press a button or turn a knob or things of that sort. It's supposed to do a specific function. If not, something's going on with the system, and we have to capture it there and then. Uh, all this cumulates or comes together with what's called flight readiness review, and that's a major review in phase D, basically saying that is everything ready? Flight systems. I haven't been covering much about the ground systems, but the ground systems, while this system is being developed, ground systems are also doing their own systems engineering in terms of developing all the displays, all the computing power they're going to need to capture all the data coming from the vehicle. And also, they're developing things like, for example, flight rules. Okay, so flight rules are basically um, what how are we going to operate this system when it's getting ready to launch? Something called launch commit criteria says if we lose two of the engines before we launch, we are no go for launch. If we lose a display, um, then we are go for launch. So there's a lot of if and then and else, a lot of if this happens, will we launch or not? And the same thing when you dock. Uh, there's a commit criteria when you're going to dock before you dock. Like for example, on the commercial crew program SpaceX, before they dock to the International Space Station, a lot of systems are check out. The Dragon is just at a hold point. Here's a station, and they do a lot of checkouts. And if everything works properly, then they dock. Even when they get ready to dock, if something goes wrong, there's something called breakaway, where they press a button and the SpaceX breaks away from from docking. So lots of work, not just on the flight systems, but also ground system. And then we go to key decision point P. I'm sorry, E. It's all systems go for support and launch operations. So now we're finalizing all the systems coming together, assembling them at the Kennedy Space Center or Boca Chica for SpaceX. All these places are starting to bring in the hardware, the spacecraft systems, and they're starting to integrate it and getting ready to launch all these systems. And then, we now have phase E. This is mission operations. These are things that are ongoing. Like, for example, here's the picture again of the Artemis Mars mission, Artemis for Mars, preparing for Mars. And so each one of these is a different part of operations, so that's going to be happening over time. not at the same time, but incrementally, we're going to have different parts of a mission happening. But in the end, we're going to have a final system, if you will, integration and operation and mission operation. And all the data happening before then is being acquired and learning from that. And so this also includes communications, okay? And this also is another area of systems engineering challenges is how we're going to communicate with the different um, spacecrafts, especially as we start going to Mars. You're going to have them, you're going to have Earth with low Earth orbiting things like, for example, the SpaceX refuel depot, and then you have lunar orbit, where you're going to have Orion and SpaceX Human Lander System, and then when we start going to Mars, we're going to have transmission and communications with vehicles there on the surface, back to the moon, back to Earth, and asteroids and other things. So it can get quite complex. And one of the major challenges is right now the Deep Space Network is being heavily, uh, well, the term is taxed. Basically, a lot of people are using the Deep Space Network, so it's starting to reach its maximum capability of transmitting information. So that's another challenge that we have. And of course, the launcher systems down here, Space Launch System, this SpaceX system, and the Blue Origin system, as well as I didn't put here, but one day we're going to have launcher systems from other countries, India, Pakistan, other countries. They're going to participate, and it's going to take a lot of countries to go to Mars. It's not just the United States and NASA. It's going to be very expensive and very challenging. So we're going to need the talent and capabilities of people from all over the world to make this happen. Um, so one of the things I just want to bring up here is that all through this systems engineering process that I've been talking about, uh, basically has somewhat of a, I don't want to say simplistic meaning, but in the end, what we're trying to do is through systems engineering is minimize or trying to reduce the likelihood of a hazard happening in space. And so this is something that was developed by James Reason back in 1990 called human error. And basically he called it the Swiss cheese model. And of course, mine's are circular Swiss cheeses, but the reason for that is because they're rotating in time. Basically, he said that a hazard can be prevented if something, what's called a barrier, catches it in time before it becomes an accident. So what you're seeing here is barriers in terms of things like good requirements, good design, good safety reviews, good training, good maintenance, crew health, culture, organization. But we're not perfect, and so there are holes, and each hole and the barrier represents a deficiency. Something was missed, and then the barrier spinning represents a deficiency that appears in a period of time. So here's an example of a hazard that happened, but it got deflected in the safety. Safety saw it and said, "Whoa, wait a minute. Uh, if you press this button with that button enabled, it's going to cause a hazard." So that hazard was deflected here. Same thing over here. Another hazard, whether it's a software bug or whatever, is deflected by a requirement. So if you have these barriers and you're able to minimize the number of holes, there's a high likelihood that you're going to prevent a hazard. But there's that rare case where all the holes line up and nothing stopped that hazard from creating an accident. And that's what we're trying to do as part of systems engineering, is making sure that we cover as much as we can in terms of potential hazards and errors. And that's why we spend a lot of time, a lot of money doing testing, and testing, especially test as you fly as you test. So it's a major challenge, and it's just constantly looking for those risks and mitigating them to prevent these kind of hazards. So in summary, future human spaceflight missions are going to be complex, and they're going to require a lot of technology, and no question about that. And the challenges both for the system as well as the human, and the use of systems engineering is going to be critical in developing this mission. So no, there's obviously there's no question about that. You got to have a methodical way of developing these kind of systems. You just can't design a system, without some kind of strict, formal, rigorous process that tries to flesh out errors that could cause hazards. And then the human is just important as the software in the system. Uh, the system made up of hardware, software, and the components and all that can be pretty much deterministic. You can design it to do pretty much what it's supposed to do. Humans are not deterministic. Sometimes, we don't do things like we did the first time or the second time. Sometimes we don't feel good, things of that sort. We're going to have to account for that as part of our development effort. And then, obviously, I mentioned this a few times about testing. It's expensive, and sometimes project managers don't want to test. They try to avoid that, but there's so many case studies out there that show that because they didn't test, they had a failure in the project when they actually implemented it. So it's part of the game, but it's something that it's a challenge that has to be dealt with, and the only way to deal with it is some kind of formal methodical process, and that's the systems engineering process. So with that ends my presentation, and I am going to stop presenting.
Yeah, sir. So thank you for the amazing session, sir. So I have some questions here. With your permission, shall I ask now, or I would like to collect the questions? I will send you to the mail.
Uh, let's see. Oh, I'm sorry. What? Can you repeat that?
Yeah, sir. With your
There's
permission, shall I ask the questions now, or else I would like to collect the questions? I will send to you the mail.
okay. There's a little bit of static in the background.
Yeah, okay.
Can can you type it in the chat?
Sorry, sir. Sir, I will ask the questions. So, okay, I would collect the questions. I will send you to the mail, sir.
Okay.
Hello.
Yeah, I'm having there's
Yeah.
static.
Yeah, okay, okay. So, okay,
Hmm.
sir, finally, so, ladies and gentlemen, as we draw the curtains on this insightful session, I'm honored to extend our deepest gratitude to our distinguished guest speaker, Mr. George Salazar. Mr. George, your wealth of experience, depth of knowledge, and passion for the field have left an indelible mark on our understanding of NASA's system engineering process. Your journey from earning a Bachelor of Science is electrical engineering to becoming a recognized leader in telemetry, communications, and systems engineering, and serves as an inspiration to all aspiring engineers and space enthusiasts in our audience today. Your elucidations on the intricacies of the systems engineering process, coupled with real world examples from your extensive career at NASA, has provided us with invaluable insights. We now have a richer understanding of the complexities and the innovations that underpin the success of NASA's mission. We express our sincere appreciation for your generosity in sharing your time, expertise, and experiences with us today. Your commitment to innovation and excellence continues to inspire us all to reach for the stars and push the frontiers of human knowledge. On behalf of everyone present here, I extend our heartfelt thanks, Mr. George Salazar, for being with us today and for contributing to a deeper understanding of the NASA system engineering process. Your presence has made this session truly exceptional, and we look forward to applying the insights and gained as we continue our exploration of the cosmos. So thank you, sir. Thank you so much for your time and everything.
Thank you.
Thank you, sir. Thank you so much.
All right. Have a good day.
Yeah, thank you, sir. Same to you.